Hello and welcome to this lecture. In this lecture, we will start looking at applications of integration. In the previous modules, we saw what integration was, what's this Riemann sum is, and how you add up infinitesimal areas to make the total area under a curve. And that has lots of interesting different twists and differences to it and lots of applications. Okay. The first sort of application we are going to see is closely connected to area, but instead of looking at area under one curve, we will look at area between curves. Okay. Now, this is important for various reasons, and you will see that the applications will be obvious to you. So, quite often there are problems where you have to compute area where the boundaries are defined by curves and you have to find the area in the middle. Okay. So, clearly there is lots of applications there. But more interestingly, I think the techniques you will learn here in relating, how to describe a region is also important. Okay, so hope you pay attention to both of those as we go along. Okay, so here's the problem. I have two functions now. One function is f of x, which is shown by this red curve here on top, and then the other function is g of x, which is this blue curve here at the bottom. Okay. I am interested in the area between these two curves from x equals a to x equals b. So, this is the area I am interested in. X equals a is this line, which maybe in this case a could be 0. I have taken a to be equal to 0, but in general a could be anything. And then x equals b is this line, right, this vertical line here is x equals b, and between from x equal to a to x equal to b means x is greater than a and less than b, right, a less than x less than b, right, that is this this whole region. And then I want the area between f of x and g of x. So, if you have to describe this region, how will you describe that region? That region that you just saw has this basic simple description, which is x is between a and b, and then y is between g of x and f of x. Okay. So, this describes the region, okay, the region that is shown here, right. So, between x is greater than a less than b, and then y is less than f of x and greater than g of x. Okay. So, you will see in general any region is usually described by these kind of inequalities. Okay. So, these inequalities describe regions. They describe the regions in the two-dimensional graph in some sense, right, and you have to try and compute the area of that region. Okay. So, that is the problem here. How do we go? So, the idea is to basically form a Riemann sum which will be equal to this area. Previously, we formed a Riemann sum which was equal to the area under the curve, right. We divided the x axis into small delta intervals, and for each delta interval we approximated the area with the area of the rectangle, and then we did the sum, and we said when the sum converges you have the integral, and that integral is the area, right. So, we will do something very similar here, but notice what is the small adjustment we have to make to get the area under the curve. It is only a minor adjustment. We will see how that is done. So, as usual, we divide AB, the interval AB, into n regular intervals of length delta equals b minus a by n. So, that is what we do here. I have shown one such interval here. This is the interval of with delta. This a to b is divided into numerous intervals of this kind, n of this size. Okay. So, what do I do next? I will pick one value xi in this ith interval. Let us say this is the ith interval. In this ith interval, I will pick a value xi. Okay. This is very similar to how we form the Riemann sum, right. So, this is some value. You can pick this value wherever. You can pick it as a left point, end point, midpoint, any other point, it is okay. You will get the same answer anyway. We have seen that before. So, we do that. So, once you do this, this is a small infinitesimal region, right. So, here you may be able to approximate the area by a rectangle's area. Okay. What should be that rectangle? That is where the interesting thing comes. The rectangle will not be just f of x into delta, it is f of x minus g of x into delta. So, that is this area, this f of xi minus g of xi times delta. That area is this small rectangle here, and then I will add it up over all I, right. I have n intervals, I equals 0 to n minus 1. I will add up these rectangular areas over all I. This is my Riemann sum. So, these Riemann sums are very powerful to approximate these kind of areas. So, notice this height of this rectangle will keep varying with the interval, right, and that is captured by this f of xi minus g of xi, and then delta remains the same. So, you multiply by the width delta, you get this small area, and you add up all these areas from A to B, you get the Riemann sum Rn. Okay. So, hope you see that, right. X0 is a point at A, x0 is here, xn minus 1 is here, and all the way in the middle you have all these points, you add them all up, you get the area. So, once you have a Riemann sum, we can tend n to infinity and make this delta infinitesimal, and we know what will happen here. This summation will tend to the area between the curves, which is integral from A to B f of x minus g of x dx in this case, right. So, it is very, very easy to see. So, you see area between the curves, you might have already guessed it in the beginning itself, it is just integral A to B f of x minus g of x dx. Okay, simple enough formula, but you see this general method. What I want to emphasize here is this general method. Whenever you want to add up an area or a volume or anything else, and with one variable it varies a lot, right, it varies with that one variable, and you want to still be able to add it up, the best way to do it is to do these infinitesimal areas and find a formula for that, form a Riemann sum, then tend n to infinity or delta to 0 in that limit, and you get the integral. Okay. So, this is an important thing to understand. This methodology of how the integral comes is important to understand. Okay. So, I hope this is clear. So, here is a small variation here. So, what happens when the curves cross? Okay. So, previously in this example the curves did not cross, it was very easy to define the area. So, here when the curves cross, there is a problem, there is a small problem. I will tell you what that problem is. If you just integrate blindly f of x minus g of x dx from A to B, this will not work. Why will it not work? Think about this. If you do this integration, remember this integration is signed area, right, it is not actual area. So, for this part it will find this area from here to this point, and then for this part it will find negative of this area. So, instead of giving this area plus this area, you will get this area minus this area. Okay, I hope you can see that. If you do the integral A to B, simply f of x minus g of x dx, you are going to get this big area minus this small area. Okay, so I don't know, you can call this like the dolphin problem or a sparrow problem or something. It looks like that figure, right. So this is this area minus this area if you do this integral. I don't want that. No, I want the total area when the curves cross. So here I have to do one adjustment. So you have to find this intersection point C, the point at which f of c equals g of c. You have to find that, and then you have to redo this integral in this clever fashion. So what do we do? The area is actually integral from A to C f of x minus g of x. And then what do I do from C to B? I do g of x minus f of x. Notice this subtle switch here, right, between f of x minus g of x. So if you want to write it in common, one way to write it in common, this area between regions is integral A to B absolute value f of x minus g of x dx. Okay. So this will always work, right. There is no problem if you put the absolute value, but then if you have absolute value, you do not know how to integrate, no, that is a problem. So you have to find out when that absolute value is what is inside the absolute value is positive, and when it is negative, and use either plus x or minus x. Okay. So how do you deal with the absolute value? Remember, the way to deal with it is absolute value of x is equal to x if x is greater than or equal to 0, and it is minus x if x is less than 0, right. So this is the way in which we use absolute value. So that also plays along with this same type of method. So when they cross, you have to pay a little bit more attention. You have to look at where they cross and change the sign of what's inside the integration to get the correct area. Okay, I hope this is clear. So here are a bunch of problems. Okay. So first thing I would suggest, when you have to find regions specified below, right. So these regions are specified in a certain way. You have to first sketch these regions. Okay. So that is an important skill to acquire. Okay. So how do I sketch this region? So let's take this first example, 1 less than or equal to y less than or equal to 4 minus x. Let's take that example. So how do you make a diagram of this region? Okay. One method is to look at this first and then forget about the inequality and make it a equality. So this is y equals 1. The other thing is to look at this part and forget about this inequality, make it a equality, y equals 4 minus x. You sketch these two things, y equals 1 and y equals 4 minus x. Let's try that. What is y equals 1? Y equals 1 is this line, right. So, y is equal to 1, this is y equals 1. Okay. And what is y equals 4 minus x? This is the same as x plus y equals 4, or y equals 4 minus x also you can plot, right. It starts at 4, okay. So, it goes a little bit higher, maybe this is 4, let us say. At x equal to 0 it is 4. So, how do I plot a straight line? Straight line, you just have to find 2 points, right, and then write it down. One easy way of doing it is x equal to 0, y is 4, x equal to 4, y would be 0, right. At 4 this y would be 0, and you just join these two lines. Oops, sorry. Join these two lines, maybe this is 4 and that is not 4, okay. So, you get this, but what will this point be? This is y equals 1, y equals 1 corresponds to x equals 3, right. So, this is 3 comma 1, this is 4 comma 0, and that is this point, okay. Now, how do you bring out the inequalities, right. So, what is this is y equals 1, what is y less than or equal to 1, now y greater than or equal to 1, this is y greater than or equal to 1, right. So, it turns out when you draw a line like this, one region, the line divides the entire plane into two parts, right, one that is on one side and the other that is on the other side, okay. So, let me just walk you through this, this is important. This is x plus y equals 4, this is y equals 1, okay. So, any line divides the region, there is the entire plane into two parts, one side and the other side. It turns out on one side you will have one inequality, x plus y greater than or equal to 4, on the other side you will have x plus y less than or equal to 4. So, in this case you will have on this side of the line it is x plus y greater than or equal to 4. How do you check that? You take any one point here, right. If you take 1.5 here, so you will see 5 comma 0 x plus y is greater than or equal to 4, right, it is 5, right. So, it is easy to see that on this side you have x plus y greater than or equal to 4, and on this side you have x plus y less than or equal to 4, or y less than or equal to 4 minus x. So, y less than or equal to 4 minus x, you can shade it if you like, it is the area on this side, okay. Now, what about y equals 1? On clearly this is very easy, on this side is y greater than or equal to 1, on this side is y less than or equal to 1, you do not even have to check this, right. So, you get this easily. So, here you have y greater than or equal to 1, which is above this line, and y less than or equal to 4 minus x, which is to the left of this line, okay. And okay, so I need one more inequality here. Okay, so I have to change this question a little bit, that it's I have to say that x is greater than or equal to 0, otherwise I won't get a proper region. So, there is also the condition that x is greater than or equal to 0. So, x is greater than or equal to 0, again how do you figure it out? This is x equal to 0, on this side you have x greater than or equal to 0, and on this side you have x less than or equal to 0. So, I know I am to the right of this line, I am below this line, right, below this slanting line, right, I am here, I am here, I am here, and that will be this region. Okay. So, I have to find the area between x plus y equals 4, or y equals 4 minus x, this is y equals 4 minus x, and y equals 1 from 0 to 3. Okay. So, this will be the integral 0 to 3 4 minus x minus 1 dx. Okay. So, I think the most important and interesting lesson in this is not the integration is easy to do, but finding out this area, this region. Okay, given these inequalities that we had, how do you find out this region? This is an important skill to acquire. In numerous problems in science and engineering you will need this. Okay, how to describe a region in the two-dimensional plane in terms of these linear equations, just lines or maybe even more complicated curves, but for now this is very important. Given these kind of descriptions, x greater than or equal to 0, and then y between 1 and 4 minus x, you are able to nail down this region, and then you can do this integration. I will leave this as an exercise, it is easy enough to do. You can find this area, or you do not even need integration, right. This is just a triangular area, as one side is 3, another side is 3, it is a right angle triangle. So, half into 3 into 3, you will get 9 by 2 as the answer, right. You can do that very easily. Okay. I hope this is clear. So, let me just walk you through the remaining problems. It says here is maybe there are additional specifications, I am not sure, but anyway let us check this. It says x squared less than or equal to y less than or equal to x. Okay. So, how do you do this? So, this is also an interesting, y is between x squared and x. So, if you were to plot x squared, you are going to get this, right. So, x squared will look like this, and y equals x, this is y equals x squared, and y equals x will look like this, right. So, this is y equals x, and this 2 will intersect at 1, right. So, this is important, and this is just the origin 0. Okay. So, the region is, so what about the two sides? Okay. So, that is important. So, on this side it is y greater than or equal to x, and on this side it is y less than or equal to x. So, how do you check again? You just go to this side and pick this point, right. Here y is clearly, greater than or equal to x. This is 0 comma 1, this is 1 comma 0, x is greater than or equal to y. Now, what about y equals x squared? Here also what will happen, on this side you have y greater than or equal to x squared, and this side you have y less than or equal to x squared. So, the region I have is y is greater than or equal to x squared, but less than or equal to x. Okay. So, y less than or equal to x, greater than or equal to x squared. So, you see it is this part and this part. So, it is this region. Okay. So, we are able to come to that. So, this is an important skill, drawing these curves. You can use Desmos if you like, and then figuring out these regions. Desmos will give you this very, very easily. I will show you how you can do this in Desmos also. Maybe I should do that right away. I will show you, if just for confirmation, you can do it in Desmos. Let me show that to you. Let's do this very quickly. So, you can do this very, very easily. Desmos will do this, x squared less than y less than x. So, you see it is drawing that, right. So, you see that region. You can put less than or equal to if you like, to make it all solid. So, that is the curve that we had before. Okay. So, Desmos also is very good for these kind of things. Okay, let us go back to our problem here. So, I need area under this area of this region. So, I am going to integrate. So, look at the limit x equal to 0 to 1, and x comes on top and x square comes on this side, and you have to do dx. So, this is something you have to calculate. This will just be x squared by 2 between 0 and 1 minus x cubed by 3 between 0 and 1, and that is just 1 by 2 minus 1 by 3, and that is 1 by 6. Okay, so, that is the answer. So, to me, I think the trick is to draw this region correctly, and the other things work out quite easily. So, you have to pick up this talent of being able to draw these regions. Okay. So, I am going to skip the 4th and 5th, or maybe I will do one of those two. So, let me do the 3rd also. 3rd goes as y greater than or equal to 1 minus x and less than or equal to e power x. So, this is something e power minus x, right. So, e power minus x. So, if you remember the plot of e power minus x and 1 minus x will start here and go here, right. So, that is 1 minus x, okay, y equals 1 minus x, right. And then e power minus x, if you remember the plot, it will come out like this. At 0 it will be 1, and then at 1 it will be e power minus 1. E power minus 1 is somewhere here, right, let us say somewhere here. So, and it will be above this line. Okay. So, I am going to have a tough time drawing this properly. So, this is 45-degree slope. So, e power minus x, maybe I should draw a bit more carefully. So, e power minus x will behave like this. I will do it on Desmos maybe, so that will be much clearer. So, it will come out like that. Okay. So, here again I think I might have not defined the whole thing properly. So, it cannot be just between, so x less than or equal to 1 here. So, that will complete the picture for me in terms of what I want. So, x is less than or equal to 1. So, that this is x equals 1, this is y equals e power minus x, okay. And I have x less than or equal to 1, which means it is on this side, and y greater than or equal to 1 minus x, which is on this side, and y less than or equal to e power minus x, which is on this side. So, you have here this way, and this way, and that is this region. Okay. Let us do a quick Desmos check. Quick check on Desmos. I can go here. I don't want this region. I want x less than or equal to 1, and then I also want this other constraint 1 minus x less than or equal to y less than or equal to e power minus x. Okay. Oh, okay. So, maybe I should do this here. Okay, so looks like I have other regions here. That's not very nice. Will this work? Maybe I can say x is between 0 and 1. Okay. So, I will add this further restriction here. So, I need x between 0 and 1 to get this region, otherwise that does not work. So, let me just go back here and correct this once again. Okay. So, this region specifies exactly what we want, and x is greater than or equal to 0 is also there. So, let me just add that out. So, it is this side. And so, you do not have to bother with this part. Actually, this e power minus x will go like this, and then there is also this other part that gets added, becomes a bit messy. So, this is just the region we want. So, what will be the integral? Integral will be from 0 to 1, right. It will be e power minus x minus 1 minus x, right, minus 1 plus x if you want, right. So, that is 1 minus x, I am sorry, minus 1 minus x dx. So, this is what you will have. Okay. So, you will have to do this integration. This is minus e power minus x between 0 and 1 minus 1, that will be just x between 0 and 1, and then plus x squared by 2 between 0 and 1. So, this is easy enough to do. You will have 1 minus e power minus 1. Okay. So, this is minus e power minus x. So, you have to put the 0 first. You get 1 minus this, then this minus 1 plus half. So, you will get half minus e power minus 1 as the answer. Okay. So, that will be this integration. So, once again I think the trick is finding out this region correctly, and that comes from your ability to draw these curves, then figure out which side is positive, which side is negative. You can use Desmos for a little bit of help, but of course, in the exam you might have to do this yourself. Okay. So, here is y greater than or equal to 0 and 0 less than or equal to x less than or equal to y. So, these two I will leave as an exercise. There is a min here. So, min means how do you deal with min? So, fifth alone I will talk about. How do you deal with min? Min is actually very easy to deal with. Min or max is very easy. So, it says y is less than or equal to min of x squared comma 1 minus x. What does that mean? This actually means y is actually it is both ways I think, but anyway it does not matter. This means this is the same as y is less than or equal to x squared and y is less than or equal to 1 minus x. What else was required here? X is greater than or equal to 0. Okay, I hope this is okay. So, now if you start sketching these guys, x is positive, okay, you only need to worry about that, and then y is less than or equal to 1 minus x, you will have this, and then y is less than or equal to x squared, so you will have this, right. So, this is 0, this is y equals x squared, this is y equals 1 minus x, this is 1. At this point, okay, what will be this point? Okay, this is the point where x squared equals 1 minus x. Do you get that? So, this point is the point where x square is equal to 1 minus x. Okay. I think there is also y greater than or equal to 0, right? Oh, I have not put a y greater than or equal. Okay. So, this problem has y being positive as well. That part is something forgotten. So, 0 less than or equal to y is greater than or equal to 0. So, you will see this is the part that will work out. So, you will have this region. But then to integrate and find the area of this region, you need to know this point, and this point is x squared equals 1 minus x. Okay. So, you can solve for this quadratic equation. You will get x squared plus x plus 1 is 0, and x is minus 1 plus or minus square root of b squared minus 4ac, that is 5 by 2. Okay. And this clearly is positive if it's only if it's root 5 minus 1 by 2. So, this could be some c. Okay. So, how do you integrate this? You have to integrate from 0 to c x squared dx plus integral from c to 1 minus x dx. Do you see that? That is how you describe this region. So, now this is what is, like I mentioned, this is a non-trivial part of these kind of problems. You will have a region that is described using these equations. You have to first plot it, understand it, figure out how the integral will change. Now, notice when I do integration of this side, here I have one curve, here I have another curve, and I have to know where this point is, then go up to that point, and then after that change my curve that I am integrating, because from here it is x squared, from here from this point on it has become 1 minus x, and I have to find that exact point where it happens and then do this. Okay. So, this you can go ahead and do. I will leave it as an exercise. This is how we do. So, the non-trivial part once again is to sketch the region. Once you sketch the region, everything will fall into place. Okay. I hope the fourth problem is okay. Okay. So, anyway, you can check it out. So, these are the problems. So, this is area between the curves. So good exercise is to take many more of these kind of problems, make sure you can sketch the region, and that's a skill that will help you a lot as you go along in the rest of science and engineering. Thank you very much.